Hello, in this lecture we'll answer on two questions. In the first question, we'll find out the length of line segment DE that is equal to x. In the second question, we will find out the value of the shaded area that is inside the quarter circle. So we'll start with the first question. In the drawing, we have triangle ABC. We know that angle ABC, this angle equals to 30 degrees. Angle ACB also equals to 30 degrees, this angle. Angle BDAE, this angle equals to 60 degrees. Line segment BD equals to 5 units. Line segment EC equals to 4 units. And our mission is to find out the length of line segment DE that is equal to x. So first of all, we'll focus on triangle ABC. Actually, triangle ABC is an isosceles triangle, but here those two angles are equal to each other, okay? So here, angle ABC, triangle ABC, this angle ABC, is equal to this angle that is actually angle ACB. Both angles are equal to 30 degrees, therefore they are equal to each other. Okay, I'll repeat again. In triangle ABC, angle ABC equals to angle ACB. So those two angles are equal to each other, and we know that according to the rule that in front of equal angles in the triangle there are equal sides, we get that in front of those two equal angles in triangle ABC there are equal sides. So in front of this angle we have side AB, and in front of this angle we have side AC, and according to the rule that I mentioned, side AB must be equal to side AC in triangle ABC. Side AB equals to side AC. Therefore, actually, as I already mentioned 1 minute ago, triangle ABC is an isosceles triangle. Why? Because it has two sides that are equal to each other. This side AC is equal to side AB. So in the next step, we'll define angle EAC, we'll define angle BAD, this angle is alpha, and we'll define angle EAC as beta. So we know that the sum of the angles in any triangle, and especially in triangle ABC, is equal to 180 degrees, okay? So the sum of the angles in triangle ABC is equal to 180 degrees. So which angles we have in triangle ABC? We have this angle that is equal to 30 degrees. Plus this angle that is also equal to 30 degrees. Plus this angle that is equal to alpha according to our definition. Plus this angle that is equal to 60 degrees according to what is given us in the question. Plus this angle that is equal to beta. In total, the sum of those all angles must be equal to 180 degrees according to the rule that I mentioned. So here, this expression expresses the fact that the sum of the angles in triangle ABC is equal to 180 degrees. So here we have 30 degrees plus 30 degrees is 60 degrees, and 60 degrees plus 60 degrees is 120 degrees. plus alpha plus beta is equal to 180 degrees. So here we will subtract 120 degrees from this equation, and we will get that alpha plus beta equals to 180 degrees minus 120 degrees. It is equal to 60 degrees. So we found out that alpha plus beta equals to 60 degrees. In the next step, we will do two constructions. The first construction is that we will extend from point A. We will draw a straight line in such a way that the angle between the straight line and side AC will be equal to alpha. So here, so actually this angle, the angle between the straight line and side AC, equals to alpha according to our construction. And the second construction that we will do is that here from point C we'll draw a straight line in such a way that the angle between the straight line and side AC will be equal to 30 degrees. Okay, so actually this angle equals to 30 degrees according to our construction. In the next step we will extend the two straight lines until they intersect with each other. And we will define the intersection point of the two straight lines as point F. So actually we created here triangle AFC, and in the next step we will prove that the new triangle that we created is congruent to this triangle, triangle ABD. So I'll write it down. We will prove that this triangle, triangle ABD, is congruent to this triangle, the new triangle, triangle AFC. So why those two triangles congruent to each other? First of all, those two angles, they are both equal to alpha, therefore they are equal to each other. So I write it down. Here angle BAD, this angle is equal to this angle that is actually angle CAF, and both angles they are equal to alpha, therefore both angles are equal to alpha, therefore they are equal to each other. I'll repeat again. Angle BAD equals to angle CAF. Both angles are equal to alpha, therefore they are equal to each other. We have already proved that alpha plus beta equals to 60 degrees, therefore this angle that is equal to alpha plus beta, angle EAF, here actually side AB equals to side AC according to what we have already found out. Here AB equals to AC. We have already proved that side AB of triangle ABD is equal to side AC. Okay. And finally, those two angles, they are both equal to 30 degrees, therefore they are equal to each other. So this angle is angle ABD. and it is equal to this angle that is actually angle ACF. So here, so those two angles, angle ABD and angle ACF, they are both equal to 30 degrees, therefore they are equal to each other. So in conclusion, we actually proved that this triangle ABD is congruent to triangle AFC, according to angle side angle rule. I'll repeat again. We actually proved that triangle ABD is congruent, this is the sign of congruent, to triangle AFC according to angle side angle rule. I will explain what I mean. Here, those two angles and the side that attach to those two angles in triangle ABD are corresponding congruent to those two angles and the side that attach to those two angles in triangle AFC. Therefore, those two triangles congruent to each other according to angle side angle rule. And from the fact that those two triangles congruent to each other, we conclude two things. The first thing that we will conclude is that side BC equals to side FC. Side BD, this side, equals to side FC. Side BD in triangle ABD is equal to side FC in triangle AFC. Here, BD equals to FC according to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles congruent to each other, therefore the two corresponding sides, that is to say BD and FC, will be equal to each other. Okay, but according to what is given us in the question, side BD equals to 5 units. Here, side BD equals to 5 units. And from this equation 5 equals to BD equals to FC, we conclude that side FC is also equals to 5 units. Okay, side FC is also equals to 5 units. Here, this side equals to 5 units. In addition, the second thing that we will conclude from the fact that those two triangles can go into each other is that side AD of triangle ABD is equal to side AF of triangle AFC. AD equals to AF. I'll repeat again. Side AD of triangle ABD is congruent to side AF of triangle AFC according to the same rule that corresponding sides in congruent triangles are equal to each other. So we define side AD as A, side AD equals to A according to our definition, and from this equation A equals to AD equals to AF, we derive that side AF is also equals to A. Your side AF is also equals to A. Side AF equals to A. In the next step, we will join points E and F together by a straight line. And we will prove that the green triangle ADE, this green triangle in DE is congruent to the orange triangle AEF. Okay. I've already mentioned it before that here we have already found out that alpha plus beta equals to 60 degrees, therefore this angle F AE that is equals to alpha plus beta, it is equal to 60 degrees. Okay, this angle equals to 60 degrees according to what we have already found out. So why the green triangle is congruent to the orange triangle? First of all, here side AD equals to A. First of all, we just right now found out that side AD equals to side AF. So side AD in triangle, the green triangle, is equal to side AF in the orange triangle. Both sides are equal to A, therefore they are equal to each other. I'll repeat again. We have already found out that side AD in the green triangle is equal to side AF in the orange triangle. Actually, both sides are equal to A, therefore they are equal to each other. In addition, those two angles, they are both equal to 60 degrees, therefore they are equal to each other. So this angle, that is actually angle DAE in the green triangle, is equal to this angle, that is actually angle EAF in the orange triangle. Both angles are equal to 60 degrees, therefore they are equal to each other. I'll repeat again. Angle DAE in the green triangle is equal to angle EAF in the orange triangle. Both angles are equal to 60 degrees, therefore they are equal to each other. And finally, side AE is a common side that belongs to both triangles, so side AE equals to itself. AE equals to AE is a common side that belongs to both triangles. I repeat again. Side AE equals to side AE is a common side that belongs to both triangles. So you can see side AE belongs to the green triangle and side AE also belongs to the orange triangle. So actually we proved that the green triangle, triangle ADE, this triangle, is congruent to the orange triangle, triangle EAF. According to side angle side rule. I'll repeat again. The green triangle, triangle ADE, is congruent to the orange triangle, triangle EAF according to side angle side rule. I will explain what I mean. Here, those two sides and the angle between those two sides in the green triangle corresponding congruent to those two sides and the angle that is included between those two sides in the orange triangle. Therefore, those two triangles congruent to each other according to side angle side rule. We have two sides and the angle that is included between those two sides in the green triangle that are corresponding congruent to two sides and the angle that is included between those two sides in the orange triangle. Therefore, those two triangles congruent to each other according to side angle side rule. And from the fact that those two triangles congruent to each other, we will conclude that side DE equals to side EF. Side DE equals to side EF. Again, side DE in the green triangle is equal to side EF in the orange triangle, according to the rule that corresponding sides in congruent triangles are equal to each other. But according to what is given us the question, side DE equals to x. So here we can write down that DE equals to x according to what is given us the question. And from this equation, x equals to DE equals to EF, we will derive that side EF is also equals to x. Side EF of the orange triangle is also equals to x. Okay, in the next step, I will present to you the law of cosines, and we will implement the law of cosines in this triangle, triangle EFC. Okay, so what is the law of cosines? I've already mentioned it a couple times before, so I'll repeat on it shortly. The law of cosines is true in any triangle. So actually, you can write down here in any triangle. In any triangle, so here triangle ABC could be any triangle. This is triangle ABC. We know that side AB of triangle ABC equals to A units in its length, side AC equals to B units in its length, and the angle between side AB and side AC of triangle ABC is equal to theta, and side BC equals to C units in its length. Then in this triangle ABC, the following equation is true, that C square is equal to A square plus B square minus 2 times A times B times cosine theta. I'll repeat again, in this triangle ABC, that could be any triangle, the following equation is true, that C square equals to A square plus B square minus 2 times A times B times cosine theta. Okay, so now we will implement the law of cosines, this law in triangle EFC. So I'll copy triangle EFC in this new page and we will implement the law of cosines in this triangle EFC. Okay. This angle FCE equals to 30 degrees plus 30 degrees, that is 60 degrees. So this is triangle EFC that I copied from the original drawing. And according to the law of cosines, we get that in triangle EFC, x squared equals to 4 squared plus 5 squared minus 2 times 4 times 5 times cosine 60 degrees. I'll repeat again, in triangle UFC according to the law of cosines. X squared equals to 4 squared plus 5 squared minus 2 times 4 times 5 times cosine 60 degrees. So here we actually found out that x squared equals to 4 squared is 16 plus 5 squared is 25 minus 2 times 4 is minus 8 and minus 8 times 5 is minus 40 times cosine 60 degrees. Cosine 60 degrees equals to 1/2. So we substitute cosine 60 degrees by 1/2. So in conclusion, this expression in total equals to minus 40 times 1/2. So here we found out that x squared equals to 16 plus 25, that is 41, minus 40 over 2. Minus 40 over 2 is minus 20. So in conclusion, we found out that x squared equals to 41 minus 20. That is to say, x squared equals to 41 minus 20 is 21. So x squared equals to 21. Here we will take a root out of this equation and we get that x equals to the positive square root of 21, or in terms of numbers, it is equals to 4.58 units. And the reason that we take only the positive square root of 21 is because of the fact that x is a length, and as a length, it must be a positive number. So I repeat on the final question to this answer that x equals to either the positive square root of 21, or in terms of numbers, it is equal to 4.58 units. We finished with the first question. In the next step, I will present to you the second question. In the drawing, we have a quarter circle. Inside the quarter circle, we have a circle and a semicircle. The circle and the semicircle are tangent to each other at this point. This is their touching point. We also know that the circle and the quarter circle are tangent to each other at this point. This is their touching point. And our mission is to find out the value of the shaded area. So first of all, because of the fact that this is a quarter circle, therefore this point must be the center of the quarter circle. So we will define this point as point O, and we know that O is the center of the quarter circle. Point O is the center of the quarter circle. Okay, and in addition, because of the fact that this is a quarter circle, we know that this angle must be equal to 90 degrees. So this is a right angle. We will define this point as point B. We'll define this point as point A. Here OB and OA are the radii of this quarter circle. Okay, it is true in any quarter circle, those sides will be always the radii of the quarter circle. So here, line segment OA, this line segment, is the radius of this quarter circle. So we will define the radius of the quarter circle as capital R, therefore OA equals to capital R. Likewise, OB is also the radius of the quarter circle. So OB, therefore OB will be also equal to capital R. It is the radius of the quarter circle. And here the radius OB is tangent to this circle at point. We'll define the point of tendency of tangent OB with this circle as point M. I'll write it down. Point M is the point of tangency of tangent OB with this circle. We will define the center of this circle as point P, and we will define the center of this semicircle as Q. So point P is the center of the circle, point M is the point on the circle itself, that is to say PM is the radius of this circle, that is equal to 2 units according to what is given us the question. And we also have rule number 1 here, and actually according to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. Here, tangent AB is tangent to this circle at point M. Point M is the point of tendency. And we have the radius OM that is drawn to the point of tendency. So whenever we have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. So if AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to this rule number 1. Actually, we can implement rule number 1 in our drawing. Why? Because in our drawing, we have the radius PM of this circle that is drawn to the point of tendency. That is to say, it is drawn to point M, that is the point of tendency of tangent OB with this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent OB will be perpendicular to the radius MP. So if OB is perpendicular to MP, it means that this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. Okay, in the next step, from the center of this circle, that is to say from point P, we will draw perpendicular on QO. Okay, so here this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees according to our construction. And we will define the touching point of the perpendicular from point P and QO as point L, as L. L is the touching point of the perpendicular from point P and QO. Actually, by doing this construction, we created here quadrilateral LPOM, and inside quadrilateral LPOM we have 1, 2, 3 right angles. Inside quadrilateral LPOM we have 1, 2, 3 right angles, and the sum of 3 right angles is equal to 90 degrees times 3 is 270 degrees, plus the size of the fourth angle, that is actually angle LPM. In total, the sum of those 4 angles, they must be equal in total to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So here we will subtract 270 degrees from this equation, and we will get that the missing angle LPM will be equal to 360 degrees minus 270 degrees, it is equal to 90 degrees. So we found out that the missing angle is a right angle, it is equal to 90 degrees. This angle LPM equals to 90 degrees. So we actually found out that inside quadrilateral LPOM we have 4 right angles. And any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we will relate to quadrilateral LPOM as a rectangle. Okay, quadrilateral LPOM is a rectangle because of the fact that it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. That is to say, in rectangle LPOM, side PM must be equal to side LO. PM equals to LO according to the rule that the opposite sides of a rectangle are equal to each other. PM equals to LO. But we know that PM equals to 2 units, so we can write here that PM equals to 2 units. And from this equation 2 equals to PM equals to LO, we will derive that side LO is also equals to 2 units. Okay, here side LO is also equals to 2 units. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we will get that side LP must be equal to side OM. LP equals to OM. Repeat again, LP equals to OM according to the same rule that the opposite sides of a rectangle are equal to each other. So actually, if we define side LP as X, here side LP equals to X according to our definition, then from this equation X equals to LP equals to OM, we will derive that side OM is also equals to X. Okay, here side OM is also equals to X. In the next step, we will focus at this point, that is the touching point between the circle and the quarter circle. We will define this touching point between the circle and the quarter circle as point K. Point K is the touching point between the circle and the quarter circle. At point K, the circle and the quarter circle have an internal lunge between them. Again, at point K, this circle and the quarter circle have an internal lunge between them. That is to say, they are touching each other internally at point K. And we know that we have the rule that any circular shapes that are touching each other internally, that have an internal lunge between them, then the straight line that joins their centers together must pass through their touching point. I'll repeat again, any two circular shapes that have an internal lunge between them, then if the two circular shapes have an internal lunge between them, then the straight line that joins their centers together must pass through their touching point. In this case, their touching point is point K. So here point O is the center of the quarter circle. Point P is the center of the circle. And the straight line that joins their centers together is the straight line OP. So this straight line OP, this straight line OP must pass through the attaching point that is actually point K. That is to say, if the straight line OP must pass through point K, it means that OPK is one straight line. Okay, OPK is one straight line because of the fact that the straight line OP must pass through point K, therefore OPK is one straight line. OPK is one straight line. So if OPK is one straight line, it means that OK itself is also a straight line, of course. So you can write down that OK is a straight line. We know that OK is a straight line, but what is the definition of the straight line OK? Here, point O is the center of the quarter circle. Point K is a point on the quarter circle itself. Therefore, the straight line OK is the radius of the quarter circle. This is exactly the definition of a radius. Because of the fact that point O is the center of the quarter circle and point K is a point on the quarter circle itself, therefore OK must be the radius of this quarter circle. Therefore OK is the radius of the quarter circle, that is equal to capital R according to our definition. So actually, in conclusion, found out that OK equals to capital R, that is the radius of this quarter circle. Likewise here, we know that point P is the center of the circle. Point K is a point on the circle itself. Therefore, PK is the radius of this circle, that is equal to 2 units according to what is given as the question. So we can also write down that PK equals to 2 units, it is the radius of the circle. So in conclusion, found out that OK equals to R and PK equals to 2. And what is the length of line segment OP? The length of line segment OP, from the drawing, it is very easy to see that the length of line segment OP, it is actually equals to OK minus PK. I repeat again, the length of line segment OK equals to the length of line segment OP, the length of line segment OP equals to OK minus PK. Again, the length of line segment OP equals to OK, the length of line segment OP equals to OK minus PK. So the length of line segment OP equals to OK, OK equals to capital R, it is the radius of the quarter circle, minus PK, PK equals to 2, it is the radius of the circle. So in conclusion, we found out that the length of line segment OP equals to capital R minus 2. Okay, capital R minus 2. In the next step, I will copy the right triangle OPK in a new page, and we will implement the Pythagoras theorem on this triangle OPK, OPM. In the right triangle OPM. Okay? So we just right now found out that the hypotenuse OP of the right triangle OPM equals to capital R minus 2. This again equals to 90 degrees, according to rule number 1, of course. And OM equals to X. So this is the right triangle OPM that I copied from the original drawing. Here PM equals to 2 units, it is the radius of the circle. So we will implement the Pythagoras theorem in triangle OPM. By PT is evaluation for Pythagoras theorem. So according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is OP, therefore the square of the hypotenuse is OP squared, and it must be equal to the sum of the squares of the perpendiculars, that is to say it must be equal to PM squared plus OM squared. Okay, so according to the Pythagoras theorem, in the question number 1, we found out that OP squared equals to PM squared plus OM squared. OP equals to capital R minus 2, therefore OP squared equals to capital R minus 2 squared, and it is equal to PM squared. PM equals to 2, therefore PM squared equals to 2 squared, that is 4, plus OM squared. OM equals to X, therefore OM squared equals to X squared. So, in conclusion, we found out that according to equation number 1, R minus 2 squared equals to 4 plus X squared. Here we will open the brackets on this side of equation number 1, and we'll get that according to equation number 1, R minus 2 squared equals to R squared plus 2 squared, that is 4, minus 2 times R times 2 is minus 4R, and it is equal to 4 plus X squared. So here we have 4 on both sides of the equation, so 4 will get cancelled. And what is left from equation number 1 after we cancelled 4? What is left is actually in this side of the equation we have X squared, that is equal to R squared minus 4R. I repeat again that according to equation number 1, we found out that X squared equals to R squared minus 4R. Okay, so in the next step, we will focus at this point, that is the touching point of the semicircle and the circle. I repeat again, this point is the touching point of the semicircle and the circle. We will define the touching point of the semicircle and the circle as point T. Actually, at point T, the semicircle and the circle have an external lunge between them. Okay, I repeat again, at point T, the circle and the semicircle have an external lunge between them. And whenever two circular shapes have an external lunge between them, then the straight line that joins their centers together must pass through their touching point. That is to say, from point T. I repeat again, whenever you have two circular shapes that have an external lunge between them, then the straight line that joins their centers together must pass through their touching point, that in this case it is point T. So here point Q is the center of the semicircle. Point P is the center of the circle, and the straight line that joins their centers together is the straight line QP. And this straight line QP must pass through their touching point, that is point T. Okay, the straight line QP that joins the centers together must pass through their touching point, that is actually point T. So if the straight line QP must pass through point T, it means that QTP is one straight line. Okay, QTP is one straight line. Write it down. Line segment QTP is one straight line. So, line segment QTP is one straight line, or we can say in other words that points Q, T, and P, they are all located on the same straight line. This is exactly like saying that QTP is one straight line. So if QTP is one straight line, QP is also a straight line. Okay, QP is also a straight line. QP is a straight line. And what is the length of the straight line QP? From the drawing, it is very easy to see that the length of the straight line QP is actually equals to QT plus TP. Again, QT plus TP equals to the length of the straight line QP. I'll repeat again. QP equals to QT plus TP. Okay, so QP equals to QT. What is the length of QT? Q is the center of this semicircle. T is the point on the semicircle itself. That is to say, QT is the radius of this semicircle, that is equal to 2 units. Likewise, point P is the center of the circle. Point T is the point of the circle itself. This is exactly the definition of a radius. That is to say, PT is the radius of this circle, that is also equals to 2 units. So in conclusion, we found out that QT equals to 2 and TP is also equals to 2. So we can write down here that QP equals to QT, that is 2 units, plus TP, that is also 2 units. So in conclusion, we found out that QP equals to 2 plus 2, that is 4. So we can write here that QP equals to, the straight line QP equals to 4 units. We can write down here that QP, the straight line QP equals to 4 units. Okay? And what is the length of line segment QA? Point Q is the center of the semicircle. Point A is the point of the semicircle itself. Therefore, the length of line segment QA is the radius of this semicircle, that is equal to 2 units. And what is the length of line segment QL? From the drawing, it is very easy to see that QL equals to AO minus AQ minus LO. Again, QL equals to AO minus AQ minus LO. So I write it down. QL equals to AO minus AQ minus LO. It is very easy to see it from the drawing. So QL equals to AO, but AO is the radius of the quarter circle, that is equal to capital R. I'll repeat again on the equation. QL equals to AO minus AQ minus LO. Again, QL equals to AO minus AQ. I repeat again, QL equals to AO minus AQ minus LO. So QL equals to AO, that is the radius of the quarter circle, that is equal to capital R, minus AQ, that is equal to 2, minus LO, that is also equals to 2. So in conclusion, we found out that QL equals to capital R minus 2 minus 2, minus 2 minus 2 is minus 4. So in conclusion, we found out that QL equals to capital R minus 4 units. So we can write here that QL equals to capital R minus 4. Okay. In the next step, I will copy the right triangle QLP in a new page, and we will implement the Pythagoras theorem on this right triangle QLP. Okay. We have already found out that QL side QL equals to capital R minus 4. LP equals to X, and the hypotenuse QP equals to 4 units. As you can see here, the hypotenuse QP equals to 4 units. So, this is the right triangle, triangle QLP that I copied from the original drawing. We will implement the Pythagoras theorem on this right triangle, triangle QLP. So here, pi PT is the abbreviation for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is QP, therefore the square of the hypotenuse is QP square, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to QL square plus LP square. So QP square equals to QL square plus LP square according to the Pythagoras theorem. QP equals to 4, therefore QP square is 4 squared, that is 16. That is equal to QL square. QL equals to capital R minus 4, therefore QL square equals to capital R minus 4 square plus LP square. LP equals to X, therefore LP square equals to X square. So in conclusion, found out that according to equation number 2, 16 equals to capital R minus 4 square plus X square. Here we will open the brackets on this side of equation number 2, and we will get that according to equation number 2, 16 equals to capital R minus 4 square equals to capital R square plus 4 square, that is 16, minus 2 times capital R times 4 is minus 8 times capital R. And we have also to add here plus 6x squared. Here we have 16 on both sides of this equation, equation number 2, and so 16 will get cancelled. What is left from equation number 2 after we cancelled 16? In this side of the equation nothing is left, so we have 0, that is equals to R squared minus 8R plus X squared. So here we will add 8R to this equation, equation number 2, and we get that according to equation number 2, 8R equals to R squared plus X squared. Okay, here we subtract R squared from this equation, equation number 2, and we get that according to equation number 2, X squared equals to 8R minus R squared. So according to equation number 2, X squared equals to 8R minus R squared. But according to equation number 1, we have already found out that X squared equals to R squared minus 4R. So we have two different expressions for X squared. In the next step, we'll create a third equation that states that X squared, according to equation number 1, must be equal to X squared according to equation number 2. Okay, X squared equals to X squared. So So x squared according to equation number 1 equals to r squared minus 4r, and it must be equal to x squared according to equation number 2, that is equal to 8r minus r squared. So we found out that according to equation number 3, r squared minus 4r equals to 8r minus r squared. Here we will add r squared to this equation, equation number 3, and we will get that according to equation number 3, according to equation number 3, r squared plus r squared is 2r squared minus 4r equals to 8r. So here we will add 4r to this equation, equation number 3, and we will get that according to equation number 3, 2r squared minus 4r plus 4r is 0. So 2r squared equals to 8r plus 4r is 12r. So according to equation number 3, we found out that 2r squared equals to 12r. Here we will divide this equation, equation number 3 by 2, and we will get that according to equation number 3, 2r squared over 2 is r squared, and it is equals to 12r over 2, that is 6r. So in conclusion, we found out that according to equation number 3, r squared equals to 6r. Here we will subtract 6r from this equation, equation number 3, and we will get that according to equation number 3, r squared minus 6r equals to 0. So here we will take a common factor r out of those two expressions, and we will get that according here. So r is taken as a common factor. What is left from r squared after we took from it r as a common factor? What is left is actually r. And what is left from minus 6r after we took from it r as a common factor? What is left is actually minus 6. So in conclusion, we found out that r times r minus 6 equals to 0. So here we will have two solutions that are possible for r. The first solution is that r equals to 0, but because of the fact that r is the radius of this quarter circle, it must be a positive number, it can never be equal to 0. So we cancel this solution, and we left only with the second solution, that r minus 6 equals to 0. So here we will add 6 to this equation, and we get that r equals to 6 units. So we found out that the radius of this quarter circle equals to 6 units. Therefore, the area of the quarter circle will be equal to the area of the circle over 4. The area of the circle is pi r squared, and when we divide it by 4, we will get the area of the quarter circle. That is to say, the area of the quarter circle equals to pi r squared over 2 when r equals to 6. Okay, and what is the value of the shaded area? The value of the shaded area is equal to the area of the quarter circle minus the area of the circle minus the area of the semicircle. I'll repeat again, the value of this shaded area equals to the area of the quarter circle minus the area of the circle minus the area of the semicircle. Okay? So the value of the shaded area equals to the area of the quarter circle. We have already found out that the area of the quarter circle equals to pi r squared over 4 when r equals to 6 units, minus the area of the circle. The area of the circle is pi r squared and r equals to 2, so it is pi 2 squared. And the area of the semicircle equals to the area of the circle over 2. That is to say, it is pi r squared over 2 when r equals to 2, so it is pi 2 squared over 2. In conclusion, found out that the value of the shaded area equals to this expression. We already found out that the radius of the quarter circle R, capital R equals to 6. Therefore, capital R square equals to 6 squared, that is 36. So in total, this expression equals to 36 pi over 4. This is the area of the quarter circle minus the area of the circle is pi 2 square. 2 square is 4, and 4 times pi is 4 pi. So the area of the circle is 4 pi minus the area of the semicircle, that is equal to pi 2 square over 2. 2 square is 4, and 4 over 2 is 2, and 2 times pi is 2 pi. In conclusion, we found out that the area of the semicircle equals to 2 units, 2 times 2 pi square units. And here 36 over 4 is 9, and 9 times pi is 9 pi, so in total this expression equals to 9 pi minus 4 pi minus 2 pi. So actually in conclusion we found out that 9 pi minus 4 pi is 5 pi, and 5 pi minus 2 pi is 3 pi. So in conclusion we found out that the value of the shaded area equals to either 3 pi square units, or in terms of numbers it is equal to 9.42 square units. Okay? I'll repeat again. We found out that the value of this shaded area equals to either 3 pi square units, or in terms of numbers it is equal to 9.42 square units. We finished with the second question. In the next step I will summarize the lecture. We will start with the first question, of course. In the drawing we have triangle ABC. We know that angle ABC equals to 30 degrees, angle ACB equals to 30 degrees, angle DAE, this angle equals to 60 degrees. The length of line segment BC is 5 units, the length of line segment EC is 4 units. And our mission is to find out the length of line segment DE, that is equal to x. So we focus on triangle ABC. In triangle ABC, those two angles are equal to each other, they are both equal to 30 degrees. So here in triangle ABC, we know that angle ABC equals to angle ACB, they are both equal to 30 degrees, therefore they are equal to each other. And according to the rule that in front of equal angles in the triangle there are equal sides, we get that in front of those two equal angles we have side, in front of this angle we have side AB, in front of this angle we have side AC, and those two sides must be equal to each other because of the fact that they are located in front of equal angles. So we found out that AB equals to AC, therefore actually triangle ABC is an isosceles triangle. We also, in the next step, we defined angle BAD as alpha and angle EAC as beta. And we know that the sum of the angles in any triangle, and especially in triangle ABC, is equal to 180 degrees. So which angles we have in triangle ABC? This angle equals to 30 degrees, this angle equals to 30 degrees, this angle equals to alpha according to our definition, this angle equals to 60 degrees, and this angle equals to beta according to our definition. So this expression expresses the fact that the sum of the angles in triangle ABC equals to 180 degrees. Here 30 degrees plus 30 degrees is 60 degrees, and 60 degrees plus 60 degrees is 120 degrees. And we have in this side of the equation plus alpha plus beta, that is equal to 180 degrees. Here we subtracted 120 degrees from this equation and found out that alpha plus beta equals to 60 degrees. Then we did two constructions. The first construction is from point A, we draw a straight line in such a way that the angle between the straight line and side AC will be equal to alpha. Here, this angle equals to alpha according to our construction. The second construction that we did is from point C, we draw a straight line in such a way that the angle that will be created between the straight line and side CA will be equal to 30 degrees. Again, this angle equals to 30 degrees according to our construction. In the next step, we extended the two straight lines until they intersect with each other, and we define the intersection point between the two lines as point F. Point F is the intersection point between the two extended two lines. In this way, we created triangle AFC, and then we proved that this triangle AFC that we created is congruent to this triangle ABD. So why those two triangles can go into each other? First of all, those two angles, they are both equal to alpha, therefore they are equal to each other. Here, angle BAD, this angle equals to angle CAE, they are both equal to alpha, therefore they are equal to each other. In addition, we have already proved that side AB equals to side AC. That is to say, side AB of triangle ABD equals to side AC of triangle AFC. Okay, AB equals to AC, and finally, those two angles, they are both equal to 30 degrees, therefore they are equal to each other. So here, angle BAD equals to angle ACF, they are both equal to 30 degrees, therefore they are equal to each other. So in conclusion, we actually proved that triangle ABD is congruent to triangle AFC according to angle side angle rule. I will explain what I mean here. Here, if we focus on triangle ABD, we actually proved that those two angles and the side that attach to those two angles in triangle ABD are corresponding congruent to those two angles and the side that attach to those two angles in triangle AFC. Therefore, we proved that those two triangles can go into each other according to angle side angle rule. From the fact that those two triangles can go into each other, we derived two things. We concluded two things. The first thing is that side BD is equal to side FC. Here, side BD equals to side FC according to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding sides, that is to say BD and FC, must be also equal to each other. But according to what is given us in the question, side BD equals to 5 units. So we can write here that BD equals to 5, and from this equation 5 equals to BD equals to FC, we will derive that side FC also equals to 5 units. Here, side FC of triangle FC also equals to 5 units. And the second thing that we concluded from the fact that those two triangles can go into each other is that side AD of triangle ABD is equal to side AF or triangle AFC. Repeat again, side AD equals to side AF. And if we, according to the same rule, that corresponding sides in congruent triangles are equal to each other. And if we define side AD as A, here side A equals to A according to our definition, then from this equation A equals to AD equals to AF, we derive that side AF is also equals to A. Here side AF of triangle AFC is also equals to A. In the next step, we join points E and F together by a straight line, and we prove that the green triangle is congruent to the orange triangle. But before that, we actually proved that in the orange triangle, angle alpha plus beta equals to 60 degrees. That is to say, this angle AFE of the orange triangle, that is equal to alpha plus beta, is equal to 60 degrees. Okay, so why the green triangle is congruent to the orange triangle? First of all, we just right now proved that side AD equals to side AF. Side AD equals to side AF equals to A. In addition, those two angles, they are both equal to 60 degrees, therefore they are equal to each other. Here, angle DAE in the green triangle equals to angle EAF in the orange triangle. Those angles are both equal to 60 degrees, therefore they are equal to each other. And finally, side AE is a common side. It belongs to both the green triangle and also to the orange triangle. Therefore, side AE equals to itself, AE equals to AE is a common side that belongs to both triangles. So we actually prove that the green triangle, triangle ADE, is can go into the orange triangle, triangle EAF according to side angle side rule. What I explain what I mean here. Those two sides and the angle between them in the green triangle are corresponding congruent to those two sides and the angle that is located between them in the orange triangle. Therefore, the green triangle is congruent to the orange triangle according to side angle side rule. We have two sides and the angle between them in the green triangle that are equal to two sides and the angle between them in the orange triangle. Therefore, those two triangles can go into each other according to side angle side rule. And from the fact that those two triangles can go into each other, we conclude that side DE in the green triangle is equal to side EF in the orange triangle. Here DE equals to EF according to the rule that corresponding sides in congruent triangles are equal to each other. But according to what is given as the question, side DE equals to X. Here we can write down that D equals to X, and from this equation X equals to D equals to EF, we will derive that side EF is also equals to X. Okay, here side EF of the orange triangle is also equals to X. In the next step, I actually presented to you the law of cosines, and we implemented the law of cosines in this triangle, triangle EFC. What is the law of cosines? The law of cosines is true in any triangle. Here we have triangle ABC that could be any triangle. Side AB equals to A units in itself, side AC equals to B units in itself, and the angle between side AB and side AC is theta, and side BC equals to C units in itself. Then according to the law of cosines, we get that the following equation is true, that C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. Again, C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. Then we implemented the law of cosines in this triangle, triangle EFC. I copied the right triangle EFC, I copied this triangle, it is not the right triangle, I copied this triangle, triangle EFC in this new page, and we implemented the law of cosines in this triangle, triangle EFC. So according to the law of cosines, here angle FCE equals to 30 degrees plus 30 degrees, that is 60 degrees, side FC equals to 5 units, side EC equals to 4 units, and side FE equals to X, that is the line segment that we are looking for. So according to the law of cosines in triangle EFC, X squared equals to 4 squared plus 5 squared minus 2 times 4 times 5 cosine 60 degrees. I repeat again, X squared equals to 4 squared plus 5 squared minus 2 times 4 times 5 times cosine 60 degrees according to the law of cosines, of course. So here X squared equals to 4 squared is 16, plus 5 squared is 25, minus 2 times 4 is minus 8, and minus 8 times 5 is minus 40. So it is minus 40, and cosine 60 degrees is 1/2, so we substituted cosine 60 degrees by 1/2. So in total, this expression equals to minus 40 times 1/2. So here we have X squared that is equals to 4 squared that is 16, plus 5 squared that is 25, minus 40 over 2 is minus 20. So in conclusion, we found out that X squared equals to 16 plus 25 is 41, and 41 minus 20 is 21. So in conclusion, we found out that X squared equals to 21. Here we took a root out of this equation and found out that X equals to the positive square root of 21. And the reason that X equals to only the positive square root of 21 is because of the fact that X is a length. It must be a positive number, it can never be a negative number. Okay, so X must be equal to the positive square root of 21, or in terms of numbers, it is equal to 4.58 units. Here, X, the length of line segment DE that is equal to X, it is equal to either to the positive square root of 21, or in terms of numbers, it is equal to 4.58 units. We finish with the first question. in the next step, I presented to you the second question. Here, in the second question, we have in the drawing we have a quarter circle. Inside this quarter circle, we have a circle and a semicircle that are tangent to each other at point T. And we also know that the circle is tangent to the quarter circle at point K. And our mission is to find out the value of the shaded area. Okay? So, first of all, because of the fact that this is a quarter circle, this point must be the center of the quarter circle. Here, point O is the center of the quarter circle. Angle LOM, this angle must be equal to 90 degrees. And there, side AO and side OB, they are both the radii of the quarter circle. We define the radius of the quarter circle as capital R, therefore AO equals to capital R, and OB also equals to capital R. They are both the radii of the quarter circle, that is equal to capital R according to our definition. And we also have here the radius OB is tangent to this circle at point M. Point M is the point of tendency between tangent OB and this circle. Point P, we define point P as the center of this circle. We define point Q as the center of the semicircle. So point P is the center of the circle. Point M is the point of the circle itself. Therefore, PM is the radius of this circle, that is equal to 2 units according to what is given us the question. And we have also here rule number 1. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So here tangent AB is tangent to this circle at point M. Point M is the point of tendency of tangent AB with this circle. We have the radius OM that is drawn to the point of tendency. Whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. So if AB is perpendicular to MO, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to this rule number 1. We can implement rule number 1 in our drawing, because in our drawing we have the radius PM that is drawn to the point of tendency, that is to say it is drawn to point M, that is the point of tendency of tangent OB with this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent OB must be perpendicular to the radius MP. So if OB is perpendicular to MP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. Then, from point P, that is the center of this circle, we draw perpendicular on QO. So this angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point P and QO as L. Okay? Actually, by drawing the perpendicular from point Q, by this construction, we created the quadrilateral LPOM that has 1, 2, 3 right angles. Okay, inside quadrilateral PLOM, we have 1, 2, 3 right angles, and the sum of 3 right angles is 90 times 3 is 270 degrees. Plus the size of the fourth angle that is actually angle LPM. This angle, in total, the sum of those 4 angles must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Here we subtracted 270 degrees from this equation and found out that the missing angle LPM equals to 360 degrees minus 270 degrees. It is equal to 90 degrees. It is a right angle. So this angle is a right angle. So we actually found out that inside quadrilateral LPOM we have 4 right angles. And any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we will relate to quadrilateral LPOM as a rectangle. But we also know that the opposite sides of rectangle are equal to each other. So that is to say, the opposite sides of rectangle POM must be equal to each other. It means that PM must be equal to LO. PM must be equal to LO according to the rule that I mentioned. But PM equals to 2 units. It is the radius of this circle. So PM equals to 2, and from this equation 2 equals to PM equals to LO, we will derive that LO is also equals to 2 units. Here LO equals to 2 units. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we will get that LP equals to OM. LP equals to OM, and if we define side LP as x, here LP equals to x according to our definition, then from this equation x equals to LP equals to OM, we will derive that OM is also equals to x. OM is also equals to x. Okay? In the next step, we focused at this point K. Point K is the touching point between the circle and the quarter circle. At point K, the circle and the quarter circle have an internal notch between them. That is to say, at point K, they are touching each other internally. And whenever you have two circular shapes that are touching each other internally, or whenever you have two circular shapes that have an internal notch between them, then the straight line that joins their centers together must pass through their touching point. That is to say, it must pass through point K. Okay, I repeat again, whenever you have two circular shapes that have an internal notch between them, then the straight line that joins their centers together must pass through their touching point. In this case, it is point K. Okay, so here, point O is the center of the quarter circle. Point P is the center of the circle. And the straight line that joins their centers together is the straight line OP. According to the rule that I mentioned, the straight line OP must pass through point K. That is to say, if the straight line OP must pass through point K, it means that OPK is one straight line. Okay, here OPK is one straight line. Or you can also say that points O, P, and K, they are all located on the same straight line. Okay, so if OPK is a straight line, then OK must be also a straight line. So here, according to our conclusion, OK is a straight line. But what is the definition of the straight line OK? Point O is the center of the quarter circle. Point K is a point on the quarter circle itself. This is exactly the definition of a radius. That is to say, OK is the radius of this quarter circle. Very simple. So if OK is the radius of the quarter circle, it means that is equal to capital R, because the radius of the quarter circle equals to capital R, so OK equals to capital R. Likewise, here point P is the center of the circle. Point K is the point of the circle itself, therefore PK is the radius of this circle that is equal to 2 units according to what is given as the question. So in conclusion, we found out that OK equals to capital R and PK equals to 2. And what is the length of line segment PO? From the drawing, it is very easy to see that PO equals to KO minus KP. Again, PO equals to KO minus KP. Repeat again, OP or PO, it is the same, equals to OK minus PK. Okay, PO equals to OK minus PK. So OP equals to OK, that is equal to capital R. According to our definition, it is equal to the radius of the quarter circle that is equal to capital R, and Kp equals to 2, it is the radius of the circle. So in conclusion, we found out that the length of line segment OP equals to capital R minus 2. Then I copied the right triangle OPM in a new page and implemented the Pythagoras theorem on this right triangle OPM. So this is the right triangle OPM that I copied from the original drawing. We just right now found out that the hypotenuse OP equals to capital R minus 2. Here PM equals to 2 units, it is the radius of the circle, and OM equals to X. So we implemented the Pythagoras theorem on this right triangle, triangle OPM. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is OP, therefore the square of the hypotenuse is OP squared. It must be equal to the sum of the squares of the perpendiculars. It must be equal to PM squared plus OM squared. Okay, so OP equals to capital R minus 2, therefore OP squared equals to capital R minus 2 squared, and it is equal to PM squared. PM equals to 2, so PM squared equals to 2 squared, that is 4, plus OM squared. OM equals to X, therefore OM squared equals to X squared. So here we open the brackets of this equation number 1, and this side of equation number 1, and found out that R minus 2 squared equals to R squared, plus 2 squared, that is 4, minus 2 times R times 2, that is minus 4R. And it is equals to 4 plus X squared. Here we have 4 on both sides of the equation, so 4 will get cancelled. And what is left from equation number 1 after we cancelled 4? What is left is actually, here we found out that according to equation number 1, X squared equals to R squared minus 4R. Okay, so according to equation number 1, X squared equals to R squared minus 4R. Then we focused and this point, that is the touching point between the semicircle and the circle. We define the touching point between the semicircle and the circle as point T. So at point T actually, the circle and the semicircle have an external knot between them at point T. That is to say they are touching each other externally at point T. Okay, and repeat again, at point D, the circle and the semicircle are touching each other externally. And whenever you have two circular shapes that have an external knot between them, like in this drawing, then the straight line that joins their centers together must pass through their touching point. I repeat again, whenever you have two circular shapes that have an external knot between them, then the straight line that joins their centers together must pass through their touching point. In this case, it is point T. Okay? Here, point P is the center of the circle. Point Q is the center of the semicircle. And the straight line that joins their centers together is the straight line QP. And according to the rule that I mentioned, the straight line QP that joins their centers together must pass through their touching point, that is point T. That is to say, QTP is one straight line. Because of the fact that the straight line QP must pass through point T, it means that QTP, it means that the line segment QTP is one straight line. So here, line segment QTP is one straight line. And we also can say, in other words, that points Q, T, and P, they are all located on the same straight line. It is exactly like saying that line segment QTP is one straight line. So if QTP is one straight line, it means that QP itself is also a straight line. So we can write down that QP is a straight line. And what is the length of the straight line QP? The length of straight line QP, it is very easy to see from the drawing that QP equals to QT plus TP. Again, QP equals to QT plus TP. Here, QP equals to QT plus TP. So what is the length of QT? Q is the center of the semicircle. T is a point on the semicircle itself. This is exactly the definition of a radius. That is to say, QT is the radius of the semicircle that is equal to 2 units. And what is the length of line segment PT? P is the center of the circle. T is the point on the circle itself. Therefore, PT is the radius of this circle that is also equals to 2 units. So in conclusion, I found out that QT equals to 2 units and TP also equals to 2 units. Here, QP equals to QT plus TP, but QT equals to 2 units and TP also equals to 2 units. So in conclusion, I found out that QP equals to 2 plus 2, that is 4. So we found out that the straight line QP equals to 4 units. Here, QP equals to 4 units. Then we found out the value, the length of line segment QA. Q is the center of the semicircle. A is the point of the semicircle itself, therefore QA is the radius of this semicircle that is equal to 2 units. And what is the length of line segment QL? It is very easy to see from the drawing that QL equals to AO minus AQ minus, again, QL equals to AO minus AQ minus LO. Again, QL equals to AO, that is the radius of the quarter circle, minus AQ, that is the radius of the semicircle, minus LP, that is equal to 2 units. I'll repeat again that QL equals to AO, that is capital R, that is the radius of the quarter circle, minus AQ, that is the radius of the semicircle, that is equal to 2 units, minus LP, that is equal also to 2 units. So in conclusion, we found out that QL equals to capital R minus 2 minus 2, minus 2 minus 2 is minus 4, so in conclusion, we found out that QL equals to capital R minus 4. Here, QL equals to capital R minus 4. In the next step, I copied the right triangle QLP in a new page and implemented the Pythagoras theorem on this right triangle QLP. Okay, so this is the right triangle QLP that I copied from the original drawing. We just right now found out that QL equals to capital R minus 4. The hypotenuse QP equals to 4 units. Here, QP, the hypotenuse QP equals to 4 units. And LP equals to X. And according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, QP square, it is the square of the hypotenuse, must be equal to the sum of the squares of the perpendiculars. It must be equal to QL square plus LP square. QP equals to 4, therefore QP square equals to 4 squared, that is 16. QL equals to R minus 4, therefore QL square equals to R minus 4 square, plus LP square. LP equals to X, so LP square equals to X square. So in conclusion, according to equation number 2, we found out that 16 equals to R minus 4 square plus X square. Here we open the brackets on this side of equation number 2, and we found out that according to equation number 2, 16 equals to R minus 4 square. R minus 4 square equals to R square plus 4 square, that is 16, minus 2 times R times 4 is minus 8R plus X square. Here we have 16 on both sides of the equation, so 16 will get cancelled. So what is left from equation number 2 after we cancel 16? What is left is that in this side of the equation nothing is left, so we have 0. That is equals to R square minus 8R plus X square. Here we added 8R to this equation and found out that 0 plus 8R is 8R. And it is equal to R square plus X square. So in conclusion, according to equation number 2, 8R equals to R square plus X square. Here we subtracted R square from this equation number 2, and finally we found out that X square, according to equation number 2, X square equals to 8R minus R square. This is according to equation number 2, but according to equation number 1, we have already found out that X square equals to R square minus 4R. So we have two different expressions for X square. Then we created equation number 3 that states that X square according to equation number 1 must be equal to X square according to equation number 2. That is to say, X square according to equation number 1 is R square minus 4R, and it must be equal to X square according to equation number 2, that is 8R minus R square. So in according to equation number 3, we found out that R square minus 4R equals to 8R minus R square. Here we added R square to this equation number 3, and we found out that according to equation number 3, R square plus R square is 2R square minus 4R equals to 8R. Here we added 4R to this equation number 3, and we found out that 2R square, 4R minus 4 is 0, and here equals to 8R plus 4R is 12R. So according to equation number 3, we found out that 2R square equals to 12R. Here we divided this equation number 3 by 2, and we found out that 2R square over 2 is R square, and 12R over 2 is 6R. So according to equation number 3, we found out that R square equals to 6R. Here we subtracted 6R from this equation number 3, and we found out that R square minus 6R equals to 0 according to equation number 3. Here we took R as a common factor out of those two expressions. So r is a common factor. What is left from r square after we took from it r is a common factor? What is left? It is actually r. And what is left from minus 6r after we took from it r is a common factor? What is left? It is actually minus 6. So in conclusion, we found out that according to equation number 3, r times r minus 6 equals to 0. So here we will have two solutions that are possible for r. The first solution is r equals to 0, and the second solution r minus 6 equals to 0. So according to the first solution to this equation, r equals to 0. But because of the fact that r is the radius of this quarter circle, it can never be equal to 0. It must be a positive number. Therefore, we will cancel this solution, and we left only with the second solution, that r minus 6 equals to 0. Here we added 6 to this equation and found out that r, that is the radius of the quarter circle, it is equal to 6 units. Therefore, the area of the quarter circle will be equal to the area of the circle over 4. The area of the circle is pi r square, and pi r square over 4 will be equal to the area of the quarter circle when r equals to 6. So the area of the quarter circle equals to pi r square over 4. And what is the value of the shaded area? The value of the shaded area equals to the area of the quarter circle minus the area of the circle minus the area of the semicircle. I'll repeat again. The value of this shaded area equals to the area of the quarter circle minus the area of the circle minus the area of the semicircle. We have already found out that the area of the quarter circle equals to pi r square over 4 when r equals to 6 units. The area of the circle equals to pi r square and r equals to 2, therefore it is equals to pi 2 square. And the area of the semicircle equals to the area of the circle, that is 2. That is to say it is equals to pi r square over 2 and r equals to 2, so it is pi 2 square over 2. Here we know that r equals to 6 units, therefore pi r square, r square is 6 squared, that is 36. So in conclusion, in total, this expression equals to 36 pi over 4. And here we have pi 2 squared, 2 squared is 4, and 4 times pi is 4 pi. So the area of the circle equals to 4 pi, and the area of the semicircle is pi 2 squared over 2. 2 squared is 4, and 4 over 2 is 2. 2 times pi is 2 pi, so the area of the semicircle is 2 pi. Here 36 over 4 is 9, so in total this expression equals to 9 pi minus 4 pi minus 2 pi. It is the value of the shaded area. 9 pi minus 4 pi is 5 pi, and 5 pi minus 2 pi is 3 pi. So in conclusion, we found out that the value of the shaded area equals to either 3 pi square units, or in terms of numbers, it is equals to 9.42 square units. I'll repeat again. The value of this shaded area equals to either 3 pi square units, or in terms of numbers, it is equal to 9.42 square units. Okay? Thank you very much.